Hello, welcome to Maths with EJD. Interestingly, I'm going to do a reproof of n into n+1 into n+2 as an integer multiple of 6, especially because of the inductive step, which I think could be done more accurately. Thanks to somebody who made a comment, and I really appreciate that. That is at EKEEBOBS7520. Okay, you know what he said? I don't know, maybe he or she said, hello there, nice video. I just want to make a suggestion on demonstrating that 3 into k plus 1 into k plus 2 is a multiple of 6. Remember that you are writing a proof, so examples do not prove it. You know, what I did before was I'll put a value here, and show you that at the end of the day, 6 can divide it. That was what I did initially, right? So it says 6k is an integer greater than or equal to 1. You can consider even and odd cases, and it actually went ahead and did a very, very, very convincing proof. And I really, these are the kind of feedback I like. So because of that, I'm doing this. I want to, not like what I did before was wrong, but based on what he said now, it can be better. It can be better. And I sincerely shout out to at AKEBobs7520. Thank you so much for your comment. I really appreciate it. So because of your comment, I'm going to do it more accurately because I believe in excellence. Okay, so let's go and do this. So the question is simple. We just want to show that we want to show that we want to show or to prove rather by mathematical induction, we want to prove that n into n+1 into n+2 is an integer multiple, of 6. That's what we want to do. So we've done, I mean, it's not new. We've done a lot of this. So, but I mean, I like to be excellent. That's why I'm having to do this again. Okay, so of course, the claim again. The claim is that uh n into n+1 into n+2 is an integer for all n greater than or equal to 1. That is for all natural numbers. So let me put that here, for all n greater than or equal to 1. That's the point. So that's the claim, right? So of course, the first thing we get to do is the inductive step. We do the inductive step, right? So we do the base step, or the base step. So the base step is to just put values, like that, and check if if we actually have integers of 6. So for instance, we say at n equals 1, right? We have 1 into 1 plus 1 into 1 plus 2, and that is equal to 1 into 2 into 3, and that is actually 6, which is 6 multiplied by 1. So that is actually an integer multiple of 6, all right? So that one is okay, but I can go further and say at n equals 2, so we have 2 into 2 plus 1. Of course, we are following this expression. So 2 into 2 plus 1 into 2 plus 2, and that is equal to 2 into 3 into 4, which is 24. Again, that is equal to 6 multiplied by 4. Just one integer multiple of 6. Then we go ahead to talk about the inductive hypothesis. The inductive hypothesis, let me color code now. So for the inductive hypothesis, we just assume. So assume the claim is true. Assume the claim is true for n equals k. So all we can do with that is to say k into k plus 1 into k plus 2 is equal to 6j, you know, of course, where j is an integer, is any integer at all, you know. So j is an integer. So now that we are done with that, the next thing we want to do is to do the final showdown, which is the inductive step or the inductive stage, whatever. So let's talk about the inductive step. So for the inductive step now, we want to prove the claim. We want to prove the claim for n equals k plus 1. So what that means is that everywhere you have k, you're going to have k plus 1. So from here now, you have k into k plus 1 into k plus 2 equals 6j. So now for every k, so for this k now, we have k plus 1. The next one, you have k plus 1, right? So that is k plus 1 plus 1, you know. Normally it was k plus 1. So it now, for every k, you have k plus 1. Then again into k plus 2. So for k plus 2, you have k plus 1 plus 2. So here, we cannot boldly write it as 6 anything because we have to prove it. So here, we have k plus 1 into k plus 1 plus 1 into k plus 1 plus 2, all right? And then we go on to have k plus 1 into k plus 2 into k plus 3. So at this point, we have to make a smart move. And the smart move is all about, so since we had k plus 1 and k plus 2 in the initial case, so I can already see here that if you can multiply the 2 through by k plus 3, we can have what we started with, that k into k plus 1 into k plus 2. So that's what I'm going to do. So I'm just going to bring k plus 3 back here, bring k plus 3 back, and then I have k plus 1 into k plus 2. So that I have now, so k multiplies everything. So I have, let me come down. Okay, let me erase this. So I have k into k plus 1 into k plus 2. So that's for the first part. So for the second one now, I have 3 multiplying everything again. So that's plus 3 into k plus 1 into k plus 2. So, you know what I did yesterday in the last video was to, of course, we already know that this is a multiple of 6, right? An integer multiple of 6, because we already knew from that assumption part from the deductive hypothesis, we already knew that this is equal to 6j, all right? We had to assume. So this is 6j. So 3 into k plus 1 into k plus 2. So what I did yesterday was, in the last video, sorry, I keep referring to yesterday. I actually did it yesterday, my time here, right? So what I did was to put 1. So if you put 1 here, you have, 1, 1. So you have 1 plus 1, 2, 2, 1 plus 2, 3. That's 3 times 2 times 3, which is an integer of 6, actually. But I mean, what, let me see his name again. What he said, what at AK EBOBS 7520 said was that since we are doing a proof, it's better. So using numbers to test it is not a very neat way to do that. And I sincerely agree with that. So here now, we need to establish actually that this is divisible by 6, that this is an integer multiple of 6. So because of that, I want to now say, so now we know this is 6j already. One part of it we already know established, but this is the other issue. So we now need to show again. So this is like a nested proof, like I told you in the introductory video. So you're trying to prove something within something you're proving. So it's more like a nested proof. So now again, we want to prove that 3 into k plus 1 into k plus 2 is an integer multiple, multiple of 6. Now, don't forget, we still have to come back here, right? Because this is, we're carrying on with the proof of k plus 1. for n equals k plus 1. So, but now we have this, and we cannot just prove by using numbers, just putting numbers to show that it is actually correct. So we have to do a convincing proof as AKE Bobs 7520. I like to acknowledge him because I really appreciate his comment. AKE Bobs 7520. I wish he has a YouTube channel so you can follow him. Maybe he will. Maybe after this video, I sincerely encourage him to have his channel also, because we need such excellent people teaching maths on YouTube. So to prove that 3 into k plus 1 into k plus 2 is an integer multiple of 6, right? So we already know that k, k is n is equal to k here. We already agreed, right? Where we came up with the issue of k. So we know k is still n, and it has to be greater than or equal to 1, So, and in that case now, we can have two cases. We can have case one where k is odd. And if k is odd, we can have something like, we can say it is 2p plus 1. This is a general expression for odd numbers. 2p plus 1. How? Because if p is 0, right? Okay, because I have an applied maths background, I wasn't really deep into all this pure mathematics stuff. So we just want to see numbers all the time. But to make it, if that makes you feel good, so put 0 here. 2 times 0 is 0, and you have plus 1. So that's an odd number, right? If you put 1, 2 times 1 is 2 plus 1, that's 3. That's another odd number. So generally speaking, this 2p plus 1 represents odd numbers. And then we have case 2. We have case 2. Case 2, that's the even case, where, of course, that's simple. We just have 2p. So at 0, 2 times 0 is 0. At 1, 2 times 1 is 2. So you have even numbers like that, going on like that. So from here, you have 1, 3, 5, and so on and so forth. AK, I'm sorry for doing this again. That's my applied maths mind talking. So, and then here you have 0 to 4, and so on and so forth. All right. So now that we know the general expressions for this, so we want to prove that 3k plus 1 into k plus 2 is actually an integer multiple of 6. So let me go color coding once again. Let me do an unusual color. This maybe green, right? Let's do green. So we have 3 into k plus 1 into k plus 2. So when k is equal to 2p plus 1, right? When k is equal to 2p plus 1, it means we have 3 into 2p plus 1. We have 3 into 2p plus 1. That's representing k now, plus the other one into 2p plus 1 plus 2. So that is equal to 3 into 2p plus 2 into 2p plus 3, right? So, and that's so sweet. And we have 3 into, 2 can be factorized there. So we have 3 into 2p plus 1 into 2p plus 3. So we have factorized 2 from here. So that is actually 6 into p plus 1 into 2p plus 3, all right? So, and with this now, this is clear. This is clearly a multiple of 6. So that we can say this is 6m, all right? This is 6m. So that is the first case now. This is case 1. So so that's where k is equal to 2p plus 1, which implies that k is odd. K is odd, all right? So that's case 1, and we have our 6m standing right there. Okay, let's do the other case 2. So case 2, we have k to be 2p. K is equal to 2p, and that implies that k here is an even number. So k is even here. K is even. So when k is even, right? So it means we have, so anyway, you see, you have k, you put 2p. So for 3 into k plus 1 into k plus 2, that would just be 3 into 2p plus 1 into 2p plus 2, right? So k is 2p, k is 2p. So that means we have 3. So again, you see 2p plus 2 is showing up here. So we have 3 times the 2 coming from here into 2p plus 1 into 2p plus 1 into p plus 1, right? Into p plus 1. And that is equal to 6 into p plus 1 into 2p plus 1 again. So, of course, allow me again to call this one 6m. Either way, so you can now go back now with what you have, that you have been able to convincingly prove that 3 into k plus 1 into k plus 2 is actually an integer multiple of 6. So let's go ahead and put everything together. So you can now say, therefore, what you started, so you can now say, therefore, what you started with was k into k plus 1 into k plus 2. So therefore, for n equals k plus 1, what we had was for every k, you put k plus 1. So you have k plus 1 into k plus 2 into k plus 3, is equal to where we stopped was where we had okay, let me just take the pen and write all that out again. So, that was a k into k plus 1 into k plus 2 plus 3 into k plus 1 into k plus 2. And we have been able to convincingly, okay, for assumption, we had that to be 6j. And for this part now, that's what we just finished proving. That is 6m. And of course, we say with full conviction that 6 is equal to j plus m. So it means that the claim is true for n equals k plus 1. So we can make our conclusion, 5 steps. You have the claim, you have the base step, you have the inductive hypothesis, and then you have the inductive step, which you have just concluded. So we have to reach a final conclusion. You now say, since the claim is true, for the base step or the base step and the inductive step and the inductive step, then it is true for all positive integers or for all n greater than or equal to 1. So once again, shout out to at AKEBOPS 7520. Yeah. Thank you so much for bringing this to my attention. I sincerely appreciate it. So if you have not subscribed to this channel, be sure to do that so you can always get this kind of nice videos so your math journey can be made very easy. See you in the next video as we keep enjoying maths together.